Hello, everyone. I'm Daisuke. I'm in Japan. Today, we are going to try to solve the very difficult mathematical problem, which is called Riemann zeta function. My name is Daisuke Ishii. I have a mathematics degree as a bachelor, but I didn't study much in my university days. But recently, I've been working on machine learning, AI, in IT field. So that's why I'm relearning the mathematics. And then I have a fantastic teacher, Rizwan. I've been learning mathematics from him since when? Since 1 year ago, 10 months ago, or something like that.
I guess 6 months ago.
6 months ago. Yeah. So since I'm accelerating this kind of my learning, hopefully some level of research in the future, I'm going to introduce Rizwan. Rizwan, can you quickly introduce your background?
Sure. I'm Rizwan Jangir. I'm completing my PhD in mathematics from Sabancı University, Istanbul, Turkey. And meanwhile, these days I am in Pakistan and teaching here in a university as well. So far, we are discussing many basic math problems. So we have discussed game theory, group theory, and this kind of problem. Recently, we encountered and we saw Riemann zeta function, and then we thought we can at least have a discussion on it. Maybe our discussion is helpful for someone else, or maybe we can get some ideas to get answers for this one. So first of all, I will just give a brief introduction what Riemann zeta function is. So Riemann zeta function is basically, it is more useful in number theory. And what is its main benefit or main use is to investigate the properties of prime numbers. So originally, yes, sorry.
This one. Can you see?
Exactly, I can see. Yeah. So originally, it was defined as an infinite series. So 1 plus 1 over 2 to power x plus 1 over 3 to power x and so on. Or if you just change x to the n. So when n is equal to 1, it's simple harmonic series that we already know, and which increases without bound. For example, its sum is infinite for the harmonics when you fix n is equal to 1. And when, for example, if n is smaller than 1, the sum is again infinite. We know that if you put any number smaller than 1, your denominator is going to increase, and this sum of this series is going to be infinite. So the Riemann zeta function was known to Swiss mathematician Euler in 1737. And it was studied by German mathematician Reiman.
This person.
Yeah. And first, the person who studied this one, he was a German mathematician, Bernhard Riemann. So in 1859, Riemann published a paper giving an explicit formula for the number of prime up to any pre-assigned limit, a decided improvement over the approximate value given by the prime number theorem. So after that, he gave a prime number theorem. However, Riemann's formula depend on knowing the values at which its generalized version of zeta function equals 0. So that means Riemann zeta function is defined for all complex numbers. Like you can even define it for x plus y iota, where of course iota is the negative root. So what Riemann knew that the function equals 0 for all negative even integers. For example, for -2, for -4, -6, and so on. And they called it trivial 0. Because for these number, for all the even negative integers, we get this function to be 0, and they called it as a trivial 0. And after that, it has an infinite number of 0, of course. In a critical strip of complex number between 0 and 1. So first of all, what we know that it has zeros on all negative even integers. Then it has a critical strip that we say it's complex number, and this zero infinite number of zeros.
Sorry, which part of the equation are you talking about? Are you talking about graph or equation?
Yeah, I'm talking about this infinite series.
This one, right?
Yeah, we are talking about when this zeta function has zeros. So we are talking about the zeros of zeta function.
Maybe we should show that kind of. Remember last time we were checking the visualization of like this one.
Yes. So here, for example, we have two graphs where one red line is for the imaginary part and the blue line is for the real part. And we are we are evaluating our zeta function at half plus iota x. So we are replacing n with half plus iota x. Then of course we'll see there are some numbers.
Maybe our audience is like a first timer of this Reiman Zeta, and then including the beginner of mathematics or non-mathematic people. Maybe they may explain this x-axis, y-axis, and then red one is did you say imaginary part? So this is a complex number, the combination of imaginary part like I, and then blue one is a real part of the function.
And yes, why we are discussing this half plus iota x, it's because Riemann knew that all the non-trivial zero, they are symmetric with respect to x is equal to 1/2. So you draw this line, x is equal to half. All of your non-trivial zeros, they are symmetric to that line.
So what this one is saying is I just learned this part of the visualization, the graph last time, and then red graph is the imaginary part. That's a symmetry based on the y-axis in the center, right?
Exactly. So for example, you draw.
However, blue part is a real part, and then this is like a rotation. So symmetry, how can I say symmetry but rotated?
So for example, it will be only zero when the both red and blue are zero, because they are real and imaginary part of a complex number, and a complex number is only zero when the both parts are zero. So our first zero, if you see exactly where you are zooming in, this is the point where our first zero, we are obtaining the first zero. And then you can see after that there is another part where both the blue and red one, they are approaching to zero.
Okay, first of all, let me just explain about the definition of x-axis and the y-axis. So as I said, red graph is imaginary parts. What do we mean by x-axis and the y-axis of the imaginary part?
So if you are consider R2 as a complex plane, then normally what we do, we consider x-axis as a real part and the y-axis as an imaginary part. But in this graph, it's the different story. So for every number, if you plug n is equal to half plus iota x in Riemann's function, so you will get a complex number in the form of x plus iota y. So the value of x are denoted with this blue part, and the value of y are denoted with this red part. So we are just eliminating the iota, and we are drawing two graphs for real part and imaginary part.
Okay, and then what's unique about the cross section? It's like okay, let's look at the positive x-axis. It's like maybe this is number 14. And then maybe number 21, and then the number of 25 or something. There's a cross section of red one, and then blue one is crossing in 0 of y-axis.
Yeah, this is exactly. So these are the points where they are touching the x-axis, means their values are 0. If you can see, even blue part has or more 0 than the red part, but the whole number x plus iota y can only be 0 when both x and y are 0. So I will go with the brief history again, so that our audience can knew what exactly how the Riemann hypothesis was this one. So what I said is like they already knew the trivial zeros, they were negative integers or negative even integers. Then so Riemann conjectured that all the non-trivial zeros, which are like not negative even integers, are on the critical line which is between x and is equal to 0 and x is equal to 1. So you draw a vertical line, x is equal to 0, then you draw a vertical line, x is equal to 1, and then this is called critical strip. And the Riemann, he made the conjecture that all the non-trivial zeros, they lie on this strip, and that conjecture later became as Riemann hypothesis.
So I'm not sure which part of the Riemann Zeta you're talking about. So let's look at the Riemann's history, or what about this paper, like on the number of primes less than the given magnitudes. It is important paper.
Yes, it is. Because as I already started with this one, like Riemann Zeta function is mainly has the application in number theory to investigate the properties of prime numbers.
Let me go through this one. Okay, I'm gonna read. Well, original title is German. English translation on the number of the primes less than the given magnitude is a seminal 9-page paper of Bernard Reiman, published in the November 1859 edition. And then the paper studies the prime counting function using analytic method, although it is the only paper Reiman ever published in number theory. It contains ideas which influenced thousands of researchers during the late 19th century and up to the present day. The paper consists of primary definitions, heuristic argument, and then sketches of proof, and application of powerful analytic methods. All these become essential concepts of the modern analytic number theory. So this is a pretty important paper. And then let me try to, maybe this one, if we are lucky.
Let's see.
Yes, this is it. But this is German, I think. And then we need machine learning to translate this Riemann's sketches. Of course, I cannot read. Maybe you can read.
I'm not sure, but
okay. Let me go back to the. What about this one? Yes.
Yeah.
This is and then let's look at this one, and then. Okay, this is a statement by Bernard Reiman himself. I believe that I can best convey my thanks to the owner, which is Academy has to some degree converted me through my admission as around its correspondence, if speedily make use of a permission, thereby receive the communicate investigation into the accumulation of the prime numbers, a topic which perhaps seems not wholly unworthy of such communication, given the interest which Gauss and then Dirichlet have themselves shown in the over lengthy period. Beautiful beginning. And then for this investigation, my point of departure is provided by observation of Euler that the product of this one, pi.
This is a notation of the product. This like summation is the sigma is the notation for the sum. So this is what mathematicians use for the product. And it says like if you keep multiplying these numbers, so you will eventually get this series 1 over n to the power s.
Yeah, looks like a useful equation. And then if the one substitutes for the p or prime numbers and for the n or whole numbers, the function of the complex variable s, which is represented by these two expressions where they converge, I denote by zeta s. Both expressions converge only when the real part of s is greater than 1. At the same time, an expression for the function can easily be found, which always remains valid. On making use of the equation, this equation. I don't know how to call this one in English. Can you read?
It's like the integration of e to the power minus nx and to the power s minus 1, and then you evaluate this integration from 0 to infinity. And because you can write integration in term of Riemann sum, so that they use the previous conversion of sum to the product, and they have written this equation from the equation to this product of s minus 1. So you take the values of s and taking the product for s is equal to 1, then multiply when s is equal to 2, and so on, and you divide it with n to the power s.
Okay, maybe let's look at a specific use case, which is would be following this part, and then come back to this equation. And then one first see that this one, and then if one no, consider the integral from plus infinity to plus infinity, taking the positive sense around the domain, which includes the value 0, but no other point of the discontinuity of the integrated interior. Then this is already seen to be equal to this one. Okay, provided that the many-valued function, the log arithmetic of minus x is determined so as to be the real when x is negative. Hence, okay, where the integral has a meaning just specifies. This equation now gives the value of the function zeta for the all complex number s, and then shows that this function, the one value that finite for the all finite values of the s with the exception of 1. And also that is 0 if s is equal to the negative even integer. This looks like an important part. So this will now give the value of the function zeta open number s shows that the function is one value and finite for value s with the exception of s, and then also that it is so also that is 0 if s is equal to the negative even integer. Okay.
Yeah, actually, I will like to change this. So what is Riemann zeta function? You have written this slide title. So that we already have explained. So Riemann zeta function is just this is infinite series. And after that, what was Riemann hypothesis? So Riemann hypothesis was simply that the zeros of this function. So this is your function. So zeta of s, when it is equal to 0, this was like, and Reiman, he gave this conjecture that all these zeros are on this critical line. And so far, like many of the zeros have been found, and they all are in the same line. So if one wants to prove this Riemann hypothesis, he or she need to develop some algorithm to prove this, that all the zeros of this function. So it's like, if you just think about it for a function of one variable, so for example, f of x is equal to some degree 2 or degree 3 variable. So simply you are solving a polynomial and finding where its zeros are. So that's a generalized concept here in Riemann hypothesis. So you are finding the zeros of Riemann function.
I understand. Is okay, does algorithm means same thing as the equation or something else?
These are like the different the paper we are reading. It's like how the mathematician, they have translated that hypothesis and used it.
That makes sense. Okay, let's keep reading. If the real part of S is negative, then instead of being taken in the positive sense around the specified domain, this integral can also be taken in the negative sense around that domain containing all remaining complex quantities. Since the integral taken through the values of infinity large modules is then infinity small.
Yes.
Infinitely small. Okay, infinitely small. However, the interior of this domain, the integrand has this continues only where x becomes equals to the whole multiple of plus minus 2 pi I. Okay? And then the integral is thus equals to the sum of the integral taken into the negative sense around these values. But the integral around the value of n2 pi I is equals to this one.
This one.
One obtains from this one. Okay. And then
So after evaluating those integrals, you can place their values, and this is what you will get. And then this is the relation between the zeta of s and 1 minus s.
Yeah, exactly. Okay. That's the relation between zeta and then zeta 1 minus s, which through the use of unknown properties of the function may express as follows. Okay, this one remains unchanged when s is replaced by 1 minus s. Of course, this property of the function induced me to introduce in the place of pi s minus 1 the integral, the general terms of the series sigma, whereby one obtains one convenient expression for the function zeta is in fact just the one set. Okay, then since Jacobi I now set, okay. The function is finite for all finite values of t, allows itself to be developed in the power of tt as a very rapidly converging series. Since for the value of s whose real part is greater than 1, log zeta equals to this one remains finite, and then since the same holds for the logarithm of the other factors of how to call this one?
Like
Phi.
Not even eta or zeta.
Okay. It follows that the function can also banish the imaginary part of t lies between this one and then this one. The number roots of this one whose real part lie between 0 and t is approximately this one. Because the integral taken in the positive sense around the region consisting of value of t whose imaginary part lie between half of I and then minus half of I, and then whose real part lies between 0 and t is up to the fraction of the order of the magnitude of a quantity of t 1 divided by t equals to this one. This integral, however, equals to the number of roots lying within the region multiplied by the 2 pi I. One now finds indeed approximately this number of real roots within these limits, and it is probable that all roots are real. Certainly, one would wish the stricter proof here. I have meanwhile temporarily put aside the search for this after some fleeting what do you mean by this one? Futil upon. And then it appears unnecessary for the next objective of the investigation if one denotes by alpha all the roots of the equation of this one, one can express log. So what's the conclusion of this paper is?
Let's go to the end and we can see that.
That's
last paragraph.
So indeed, the comparison
of Lie of x
with a number of prime number less than x undertaken by Gauss and then Goldschmidt and then carried to up to x equals to 3 million. X equals to 3 million. This number has shown itself out to be in the first 100,000 always less than Lie x in the factor of the difference growth with many fluctuation gradually with x, but also increase and decrease in the density of the primes from place to place that is dependent on the periodic terms has already excited its attention. Without, however, any law governing this behavior having been observed in any future accounts, it would be interesting to keep track of the influence of the individual periodic terms of expression and the density of the prime number. Density. More regular behavior than that of fx would be exhibited by the function fx, which already in the first hundreds is seen very distinctly to agree average with the x plus log zeta. So I'm not sure about this 3 million parts. How did he try 3 million numbers?
So like if you place x as a 3 million, it's still this number has shown itself out to be in the first 100,000. So it's like always less than what you will get in the Lie of x.
So these parts maybe. So Riemann zeta is about converging.
Yes, so I mean, yeah, exactly. Reiman hypothesis is like if you go a little bit up and show that series, the definition of this one. So yeah, it's like solving this series equal to 0. So you find when this equals to 0, so you need to find all those values of s. And the conjectures say all those values, they lie in critical strip. So between x is equal to 0 and x is equal to 1.
What do you mean by this one?
One second. Which one? Yeah, so this you see there is this strip of the colors there where they are matching. So these are the exactly possible answers of the 0. So if you enlarge it, it's always between x is equal to 0 and x is equal to 1.
So real part is like x-axis, and then y-axis is imaginary part, imaginary zeta.
Yes.
And then you're talking about center of this one.
It's like talking about the zeros. If you close this picture, there is description written below it.
Okay. The Riemann zeta function zeta plotted in a domain coloring. Yeah. I mean, yeah. Last time we were talking about this kind of domain coloring. Maybe audience have no idea about domain coloring. So what is domain coloring? Complex analysis domain coloring or color wheel graph is a technique to visualizing complex function, assigning color to each point of the complex plane. By assigning point to the complex plane, these different colors, brightness, domain coloring allows a four-dimensional complex function to be easily represented and understood. So this provides
because the plane is two-dimensional and visualizing 4D in 2D is not that easy. So what complex theorists do, so in complex analysis, they always like give a specific color to a particular number. For example, for zeros, there will be a specific color. When real part is going bigger, it's like changing its color, and when the imaginary part is going bigger, it's changing its color, so that the exact point in 4-dimensional can be identified using the colors.
So because color is like something like RGB, so 3-dimensional, let's say, and then this is 2D screen, so 2D plus 3D is 5D. Makes sense.
But we are representing 4D actually using the colors and using the XY plane.
XY plane. What do you mean by XY plane?
So this graph you are seeing in 2D. So this picture, it's not in but this picture is representing a 4-dimensional thing. So you are multiplying two complex number. So you have 2 dimension for first complex number and 2 dimension for second complex number.
But what the color means, like what the green means, what the pink means.
If you just see the motivation, it's given below. It will explain why these colors they are used, and this is method explain how the coloring are assigned. Before that, the motivation is given.
So what do you mean by motivation in mathematics?
Just go a little up I mean, motivation means
okay.
why
Real
motivation-
function can be
yeah,
drawn
they,
to the two-dimensional because there are two represented variable x and z. Why? However, complex numbers are represented by two variables and therefore two dimensions. That means, okay, representing a complex function, more precisely complex value function, a complex variable requires a visualization of four dimensions. One way to achieve this one, the Riemann surface, but another method is by domain coloring. So let's look at the Riemann surface.
sure.
Oh, this one. Okay. So 3D visualization plus color, I guess.
Exactly. So that makes a 4D.
But this is hard to make, I think.
Exactly. That's why the people, they more prefer more domain coloring. And now if you go back, there is a method written, we can read that. So how the people, they have what was the method to color the domain? So which number is assigned to which color? So even if you go back, we can read that. Yeah, this one above method. Before this heading, there is a method heading.
The number of choices of function, okay, the variable properties such that the inverse function is exactly as right as the original function is that possible choices include, okay, a widespread choice that was the property of the function. The approach uses HSL, hue, saturation, lightness, color model. Okay, so maybe this is a famous one. I see.
We are going cylindrical geometry.
I understand saturation and lightness, but what do you mean by hue here? Hue?
It's like how the colors is transforming to the other nearby colors.
Okay. Hue means that one. Okay. So here, hue is, what do you mean by arg? Arg?
Yeah, if you just go one heading above this one, can you scroll up? Yeah, this one, the method. Representing a four-dimensional complex mapping with only two variables is undesirable, as method like projection can result in a loss of information. However, it is possible to add variable that keeps the four-dimensional process without requiring a visualization of four dimensions. In this case, the two added variables are visual inputs such as color and brightness. Because they are naturally two variable, easily processed and distinguished by the human eye. This assignment is called color function. So they call it color function, how they assign these colors to these numbers. There are many different color function used. A common practice that is being used is given below.
I understand that. Okay, since this is just starting point, shall we look at the history of Riemann and Euler, if possible?
Sure. We can, of course, we can see that.
So his Euler, Leonhard Euler, is a Swiss mathematician, and then born in 1707, died in 1783. Swiss mathematician, physicist, astronomer, geographer. What do you mean by logician? But engineer, founded the study of graph theory and then topology, made pioneering influence of discovery in many branches of mathematics. Analytics, number theory, complex analytics, infinitesimal calculus. Okay.
Yes.
And then he introduced much modern mathematical terminology and notation, including the notion of the mathematical function. He is known for his work, mechanics, fluid dynamics, optics, astronomy, and the music theory. So he did music.
Yeah, he has like a diversity.
And then early life. Euler was born in Basel, Switzerland. The pastor of the Reiman Church. And then Margaret, another pastor's daughter. He was the oldest of 4 children, having 2 younger sisters, Anna and Maria, and Maria Magdalena, and the younger brother, Johann. Soon after the birth of Leonardo, Euler family moved from Basel to the town of Reiman, Switzerland, where his father became the pastor of the local church of the Leonhard spent most of his childhood. So in this age, maybe I think many mathematicians born in the church.
I guess so.
I think base is from the church. And then career. St. Petersburg. Around this time, Johann to son Daniel Nicholas are working at the Imperial Russian Academy of Science, St. Petersburg. Berlin. Okay. He went to Berlin Academy.
Yeah.
Personal life. Oh, what else? Eyesight worsened. Okay. Return to Russian death. Okay. So contributions
to mathematics.
So found the Euler number, of course, because name is decided after the Euler.
Yeah, also there is an Euler function as well, then Euler identity, which was your favorite one about E, pi, and...
That one. So what do you mean by notation here?
Notation?
Yeah, this one. It's a note.
Yeah, I mean the notation is like just representing. So you have seen very mathematical, like a complex terminology, and then they are representing with some simple notations. This is what he has introduced several notational conventions.
Analysis. Okay. The new So this is our equation.
Yeah.
Number theory. Graph theory. Okay, graph theory. Physics, atomic engineering. So what do you mean by engineering in this age?
In this age, engineering is like solely working on the base of physics and mathematics. Since he was providing like information to mathematics and physics, and of course that is helpful in engineering.
Logic. Music. One of the Euler's more unusual interest was application of the mathematical ideas in music. Hoping eventually incorporate musical theory as a part of mathematics in this work. Let's check this one.
Music theory.
Musicology.
Wow.
Lots of researches. Pitch, scale, mode. Okay. Consonance, dissonance. Okay.
It's like they have evolved from resonance.
Melody, chord, harmony, timbre. Timbre. Okay. Let's play this one. Spectrum, dynamics, articulation, texture, from a structure, expression, notation. Yeah, I just wondered how he used his discovery to the music.
I mean, it's like the man who has interest in almost every field. Even if he had interest in music, he said, why not to look at it as a mathematical point of view?
Yeah. That's very important. And then lastly, let's look at Van Reiman. He's very famous as well. So what do you mean by Riemann geometry?
It's again discussing Riemannian surface and this kind of complex manifold.
So I need to look at the Riemann surface. Where's the Riemann surface? Okay. Okay. Riemann geometry is a branch of differential geometry which studies Riemann manifolds, smooth manifold in the Riemann metric with inner product and then tangent space and smoothly from point to point. This gives in particular local notions, the angle, length of path, surface area, and the volume. From those, some of the global quantities can be derived by the integrating the local contributions. So in this kind of research,
yes,
I think this is valuable, but maybe I should check each theorem to see the use cases in a real world, right?
Sure, that's the important thing. If the theory is not useful, there is no benefit to like work in it or like prove something.
Okay, Riemann geometry, complex analysis. Okay, complex analysis. So here, what do you mean by real analysis?
It's like study of real numbers and everything, real functions.
Number theory. Okay. So yeah, thank you very much. So I hope, well, this is not organized, but just browsing the Wikipedia, and then my program, I don't know how to pronounce equations, symbols in mathematics, English mathematics.
But still, it's already improved from if you just compare with the beginning.
Something. I say something, but something can be wrong. But yeah, what was the most interesting point in browsing the Wikipedia today?
So yeah, it was like most important point is like the understanding the theory. So what actually the theory is, because if someone really wants to work on it, he or she first needs to understand what is the problem, because if we understand the problem correctly, maybe we can think in some direction to prove it. So that was the first point that we browse some pages, discuss some research paper or something, and even we discuss the life of those legend mathematician. And we have learned that they had interest in different fields, but they still look that field in as a mathematician. That's the important thing so far that was interesting for me in browsing these pages. Now you can give your point of view or like your interesting thing for you.
Yeah, I always enjoy reading Wikipedia, and then of course I need to skip the theorem proof, but and then also meaning the proof, but I can get the kind of rough understanding of the equation because I can see the numbers itself. And
It's more advanced. And sometimes I do not understand many of the equations because they are advanced and they're from the research of some like renowned mathematicians. It's not like the work of some my professors. Of course, I can understand that, but it takes some time to study the basics and absorb those equations. It's completely normal for everyone.
And then I can, I enjoyed reading the branch of Wikipedia, like some of the irregular parts of theory or unique category of the theory or subdivision of the theory. So that was really interesting. Also, I enjoy looking at mathematicians' history, private life, why he started this research, or why, and then how did he get appreciated within his life or after his death, or when his theory or research was implemented in real world or real life or industry, even industry, can be interesting. Reading, not understanding, but the browsing in Wikipedia. To me, it's really valuable. And then Wikipedia picture, sometimes video or audio is free to use. So this is really valuable.
They are self-explanatory. Everything in those pictures, it's like explaining itself. You can just read the picture.
Yeah. So one of my favorite concepts of the machine learning industry is open science culture. Everyone is trying to publish the paper, and then sometimes including the data itself. And then it's like a passing the baton to next person, and then next person took over, and then do continuation of the research, and then boost the research by putting them in the public.
Yes,
so,
it is.
So it is happening in the mathematics, like open science, collaboration, conference.
There are many collaborations. Like these days, the people from the computer sciences, they are collaborating with the people in mathematics, and this is how this machine learning and these kind of fields, they are evolving, and they are really helpful. Yeah, the work in the intersection of two fields is always more interesting.
I think so, because mathematics, like advanced mathematics, is highly abstract, and then very, very, very few people, maybe 0.001% of the people can understand, and then intersection of two can be 0.00001% of the people can understand. So that's.
Yeah, but it's more useful for the industry and other areas.
I think so. Yeah. Because abstract mathematics represents something in industry, and then it's like solving a puzzle. So that's hopefully we can solve a new program with combining the two mathematics concept.
Sure.
Okay, so today was our first trial, and then thank you very much for teaching me, and then I appreciate. And
it was just a discussion.
Yeah, I hope. Well, I don't think people can fully enjoy this video, but in this style, maybe we can broadcast our study and then session.
Maybe it's helpful for some people. Still, it's helpful for some people. We don't know.
Yeah, because hiring mathematics teacher is sometimes hard, and then putting this video in the public can be beneficial for someone. I hope someone can.
I hope.
Okay, thank you very much. So see you next time. Thank you.
See you. Bye.